Hello there, my name is Smith and I was in charge of the simulation role.
I'm Randy, I was in charge of sensors.
I'm Zach and I was in charge of algorithms.
I'm Ben, I was in charge of motors.
And we are Team 1 from ECE 4534, Embedded System Design, which is our senior capstone project. The purpose of this project was to create an autonomous rover capable of navigation through a room to a specific end destination without colliding with walls. So as you can see here on the whiteboard, we have a picture of a map, and the rover is placed on this side of the map, whereas the X, is the end destination placed on the other side of the map. Along the way, the rover must traverse up to 3 different ramps in a particular order. As you can see here, we have 3 different squares, each marked 1, 2, and 3. Those are our ramps, and they are labeled as such in accordance to how they must be traversed. So for example, 1 means this ramp must be traversed first, 2, and then finally 3. Each ramp has a designated entry point and an exit point, meaning that the ramp must be traversed this way and then leaves this direction. The coordinates of all the points of the map, such as the corners, ramps, and destination, are given to the rover prior to its run through the map. The rover, however, is unaware of its starting location on the map and must figure it out.
Alright, so our strategy for accomplishing this task involved first discovering the location of the rover on the map. Once this position of the rover is determined, navigating over the ramps in the correct order and finding the final destination is relatively easy to do. The method of discovering the location of the rover was to follow the perimeter of the map, keeping track of the left and right turns taken and the distances traveled between each turn. Along the way, we matched the information of previous movements along with the map data given to us. Once a unique match is found on the map, the position of the rover will have been determined.
Now before the rover can start wall following, it first has to find the wall. So to do that, it'll move towards a wall in small steps. Now once it finds itself close enough to a wall, it's going to realign itself by rotating, and then it can start wall following.
Due to time constraints, some parts of the project were dropped from our design. Ramps were entirely dropped from the project, as well as location determination based upon distances traveled. Location determination was, however, still performed with the previous history of turns, which proved to be sufficient for many kinds of ramps. Additionally, while starting from random locations on the map worked for the simulated rover, the real rover had to start next to a wall. Finally, while the real rover was quite effective at making left turns, the real rover did not always perform right turns when needed. This caused the position determination algorithm to not work effectively on the real rover.
For our rover, we chose to use 3 long-range infrared sensors. 2 are oriented facing right, and 1 is oriented facing front. The max range for these sensors is about 120 centimeters. The front sensor is used to detect walls directly in front of the rover, while the right sensors are used to wall correct, which will be explained later in the video. We chose to use infrared sensors because it does not have a conical range like the ultrasonic sensors, so there is a smaller range for error. This graph shows the voltage readings of the sensors as you move the sensor further away from an object. As you can see, distance A and distance B have the same voltage readings. Because of this, we invalidate all readings under 20 centimeters. After 20 centimeters, the voltage steadily decreases. Using this graph, we can make a formula. This converts the voltage readings, the sensor data, into a distance in centimeters.
Alright, so there are 3 main systems in this design: the rover, the arm, and then simulation. On the rover itself, there are 3 pick boards: the master pick, which has 2 slave picks, the sensor pick, and then the motor pick. Once the sensor pick calculates the sensor data in centimeters, it sends the data to the master pick using I2C. This sensor data is sent across UART to the arm pick, which then sends across to the arm using I2C once again. The arm is the brain of the system, which uses the sensor data to send motor commands. These motor commands are sent from the arm all the way back across the system to the motor pick, eventually to the motors itself, which I'll talk about more later. Bottom line though, the sensor data is sent from the sensors all the way to the arm, which sends motor commands all the way back across the system to the left and right motors. And then simulation can emulate both systems, the rover and then the arm, which helped us debug throughout this semester.
So because we have multiple components talking to each other, we need a communication protocol. Every communication protocol needs a proper message format. In our message format, we had a standard 6 bytes of data that went through every device. Our first byte of data is our start byte, which in our case was hex 0ff, or 255 in decimal. This signified the beginning of a message. Our last byte of data was 0xFE in hex, or 254 in decimal, which is used to signify the end of the message. The start and stop byte were used to prevent junk data. Our second byte is for the message type. This differentiates all the different types of data, such as the front sensor, both of our side sensors, motor commands, and acknowledgements. Our third byte of data was a sequence number, which would keep track of the order of messages being sent. So for example, if a message was received by the ARM was number 32, but expected number 31, it would recognize that a message had been dropped. Our fifth byte of data was a hash, which we used to make sure that all 6 bytes were indeed still intact. And the fourth byte was the data itself. Later on though, we took out the sequence number in favor for more data as well as the hash. However, we do not encourage future groups to employ this method because keeping a sequence number is immensely useful for debugging.
As the sensor role, I was responsible for making sure the sensors were receiving valid and accurate data and sending that data to the master PIC in our message format. To accomplish this, I sampled 5 values from one of the sensors and sent the average of those values to the master PIC. Then I sampled 5 more values from this sensor and then sent that to the master PIC. I repeat this for all 3 sensors, so I'm constantly cycling between all the sensors. Although this sounds slow, the rover is actually sampling 500 samples a second, which means it's sending 100 messages a second to the master PIC. Originally, we intended to use a line sensor to assist in detecting and traversing ramps. However, because of the removal of ramps from the final project, the line sensor was completely removed from the demonstration.
Alright, so in the motor role, I was in charge of the master PIC and the motor PIC. As stated earlier, the master PIC acts as the relay to pass along sensor data and motor commands. So when the motor PIC gets the motor commands, it is then converted to commands by which the motor controller, the saber-tooth, can execute. So for our design, we chose to use simplified serial mode. Pretty much the motor PIC sends byte values to the motor controller, which will control the left and right motors individually. Alright, so here's simplified serial mode. In essence, the left motor, it can go from 1 to 127. 1 is full speed reverse, 127 is full speed forward, 64 is stop. Anything in between these values will reverse the motor. Anything between these values will move the motor forward. And the same thing goes with right motor. 120 is full speed reverse, 255 is full speed forward. So for example, if you want to move both motors forward at full speed, you would send a 127 across UART to the motor controller, and then immediately after you would send a 255 across UART. And then so we had 4 motor commands as listed right here. The first motor command was to control each motor individually by relative speeds, 0 to 63. This was for wall correcting, so it follows along the walls parallel. And then so the second and third were rotate left and right x degrees. It goes from 5 degrees to 180 degrees, and then our final command was a distance command, which would move forward x feet.
So I was a simulation role, and I was mainly used as debugging role. In the early stages of development, the simulation was used to simulate sensor data. All the simulation was done in MATLAB, so it was fairly simple to do. The sensor simulation would send the data to the ARM through the Wi-Fi, and the simulated sensor data was not differentiable from the actual sensor data. So in essence, they were both the same thing. There was also another simulation used for reading in sensor data, and what it would do is it would read in the sensor data and print it out on the MATLAB display. This was used because we want to make sure that the sensor data we were receiving was correct and wouldn't lead to problems later on in the future. Alright, so towards the end of the class, the simulation was actually able to create a simulated rover. The simulated rover was able to read in the map format and create the map. The simulated rover had all the important aspects of the rover. Mainly, it had 3 RF sensors in place where the actual sensors would be. So what it would do is it would get the sensor data in relative to the map, and it would send the sensor data to the ARM, and the ARM would send movement commands based on the data. The simulated rover would move based on these movement commands. This was extremely beneficial in testing the algorithm before using it for the actual rover. Also, the ARM algorithm would then keep track of the number of turns to figure out where it was on the map, which will be talked about next.
The algorithm's role was responsible for reading in sensor values and sending out motor commands to navigate the rover through the map. Much of the algorithm's work pivoted upon a working wall-following algorithm. An early method of wall following involves setting the left and right speeds of the rover to certain values to always keep the rover turning towards a certain threshold distance. As you can see by this diagram, we chose 45 centimeters as our threshold. For example, with that 45 centimeter threshold, if the rover detected that it was 50 centimeters away from the wall, it would move towards the right. If instead it detected that it was 30 centimeters away, it would move towards the left. This method was not sufficient. It was heavily prone to oscillation, which you can see in this video. Later methods involved setting the left and right speeds to values that scaled with the distance away from the threshold, but that did not prove to solve the issue of oscillation. In order to create a reliable, non-oscillating wall-following algorithm, many new data points had to be taken into account. Given the two sensors on the right side of the rover, we can determine the following: the orientation of the rover with respect to the wall, the distance of the rover from the wall, and the rate at which it is moving towards or away from the wall. The third data point is determined by keeping the distance of the rover from the wall at the previous iteration of the algorithm and subtracting the current distance from it. These three data points are weighed by certain factors and added together to set the speeds of the left and right motors such that 1. The rover stays relatively straight, 2. It maintains a reasonable distance from the wall, and 3. Counteracts oscillation and does not overcorrect. You can see the resulting wall following in the following video. As you can see, it struggles a bit where the door ends, leaving the rover in a very poor orientation. The algorithm, however, quickly straightens the rover out, such that it follows the wall correctly again. Position determination was accomplished by matching the left and right turns of the rover with the left and right turns on the map given to us. The rover continues to follow walls until it finds a series of left and right turns that occur only once. At that point, the position determination algorithm knows exactly where the rover is. As you can see in this video, the arm displays a map as well as red squares in each corner. The red squares represent the corners that the algorithm believes the rover was at for its last turn. At each turn, there are less red squares drawn. This is because the algorithm is receiving more information and pinpointing the exact location of the rover. Once the position of the rover is uniquely determined, the algorithm tells the rover to continue wall following until it reaches the closest corner to the end destination. Once at that location, the algorithm tells the rover to simply rotate right forever to signify that it is done.
In essence, our rover was able to reliably wall follow and make left turns.
However, our right turns were not 100% reliable, and as a result, our position determination algorithm was not as robust as we would have liked.
However, the simulation provided an environment where the rover could make right turns, and therefore the full algorithm could run successfully.
Thank you all for listening. We hope you learned a lot, and hope to see you next year in this class.
Bye bye.